Presentation. Hello. We're going to talk about two-person games today. First, we're going to talk about games and this concept called Nash equilibrium. These are games between people, and they have strategies, and Nash equilibrium is where they settle on strategies where they decide not to change them because there's no incentive to change. Zero-sum two-person games are games where one person loses and the other person wins that same amount. Okay, so it's a little less general than games in that one person essentially pays the other person that amount. So if in any outcome. So there's mixed strategies. There's which are when you have a set of strategies, what it means is you can play a distribution over the strategies, right? So player one can play a distribution. In some sense, I'm going to talk about this again. Rock, paper, scissors. The game we're talking about is that the strategy you're talking about is you can play rock with probability 1/4, paper with probability 1/4, and maybe scissors with probability 1/2. That's a mixed strategy, and that's the kind of strategies we're actually going to be talking about is probability distributions over strategies, and each player will pick independently from that. And now these mixed strategies will have equilibriums. So we'll show you how to check equilibriums, and we're going to talk about this notion that if somebody else announces their mixed strategy, then and they tell me what it is, then I can, like if I announce that I'm going to play rock with more probability than a third, you would play paper, and you would win with more. You would win more often. And there's a duality theorem for zero-sum two-person games, and we're going to talk about that. Finally, we're going to finish up linear programs by saying that they're very general. Any circuit can be implemented by a linear program. Any polynomial time algorithm sort of corresponds to a polynomial-sized linear program. And that's basically because computers, in some sense, are circuits. So we have strategic games. Each player has a strategy set. The set S1 is the set of strategies for player one, capital S1. And now we also have a payoff function. It's a vector valued payoff function. It's a payoff for each player, assuming that the player played strategy little s1 from its strategy set of big S1, and so on. Each player plays those strategies, and then there's some payoff vector where player one gets some amount of utility, and the second player two gets some amount of utility, and so on. So here's an example where player one has a strategy set of defect or cooperate. You can think of this as two players. They could either cooperate with each other or try to go out on their own. Okay, so in some sense it was called the prisoner's dilemma. Really, what it is these players are prisoners, and they could either decide to stay silent together, and that's cooperating, or they could both they could defect and rat out their friend. So this is a classic game. So I'm making up this payoff space is that if both cooperate, if both people choose the strategies from the strategy set, cooperate, they get, each one gets 3. Okay, but now what is the best thing for the players to do? It's sort of clear what the best thing is for them to do. They both cooperate, right? That's what they should do. They both get a payoff of 3-3. All the other ones, in some sense, at least the sum of the utilities is lower. So in some sense, if they were, kind of clever, they might both cooperate. But on the other hand, look what happens. If they both decide to cooperate, and if player one wants to do better, he can do better by switching to defect. So he's going to be really tempted to go to defect, and that's what we're going to say. We're going to allow him to do what he wants, okay? And so that'll be what happens. That'll be what happens. But now in this situation, player 2 sees that she could do slightly better if she defects. So she sees that, and then she defects. So when you play these games, what happens is this is going to create incentive for both of them to narc out their friends in some sense in this cops and robbers game. Okay? So now it's stable. This is a stable point. And this is something called a pure strategy where they're stable. Both of them really aren't playing a probability distribution over cooperate and defect. They're just playing the player 1 and player 2 both will defect every time. Okay, so the Nash equilibrium in this situation, neither player has an incentive to change. For this player one, if he changes to cooperate, he only does worse. And if player two changes to cooperate, she only does worse. Okay, so now let's talk about two-person zero-sum games. Here we have a matrix A, where Aij is the payoff if the row player, we're going to have a row player and a column player. So the row player plays strategy I, and so you look at this the ith row. And the column player plays strategy J, so you look at the jth entry in the ith row. And the mixed strategy now is the row player has a mixed strategy where it's playing a distribution over x1 through xm. Okay, and the column player has a mixed strategy where she's playing y1 through strategy I with strategy 1 with probability y1, strategy 2 with probability y2, and so on. And so these are probability distributions. And now we're assuming the players play independently, just like in rock, paper, scissors. Each one is playing a probability distribution. At some point you choose rock or paper or scissors, and the other player does it too, simultaneously, without knowledge of what the other person is going to choose out of its distribution. But you do have, in this world, we're thinking about situations where you do have knowledge of their distribution, but you don't have knowledge of what happens in each time. Okay, so the payoff is in this form. It's basically, you write as a matrix form as X transpose A, Y. And the reason that is let's look at it here. The probability that player 1 plays strategy I is X sub I, and the probability independently that player 2 plays strategy J is Y sub J. So the probability that the two happen together is the product of these two probabilities, since they are independent. And now, if that happens, if player 1 plays I and player 2 plays J, column J, then the payoff in that situation is A sub ij. Okay? It's just one number. And so now we could factor this out, and now we can see that, we can factor out the xi, we could split this sum to sum over the xi's of the sum over yj of aij times yj. Right? It's just a sort of a undistributive property. Okay? And that's, and you could also see it the other way. We could have factored out the xi's and grouped them and then summed over the j. You can do this in either order. And either one of these sums, however you like to see it, is exactly this payoff. Okay, so now we're going to assume that the row maximizes and the column minimizes. So in this world, the entries correspond to how much, say, the column pays the row. So what is an equilibrium pair here? So what has to happen is, if there's an equilibrium pair, what has to happen here now is that there's no incentive for y to change. Okay, y shouldn't change in an equilibrium pair. Okay, so what it says is, whatever the payoff here for this form, whatever this payoff is, it should not do better with a different y. So the best y in the world, the best strategy in the world, should not do better, because it has no, it knows, it doesn't have an incentive to change. It knows this strategy. The column player knows the row player's mixed strategy, and then it gets to choose any strategy, and it's no better than the strategy it's using now. Okay, and similarly for the row player. The row player gets to see the other player's strategy, and it decides whether it wants to switch, and we want to say it's in equilibrium if it has no incentive to switch. And so this is the other case. Okay, so neither player has an incentive to switch. There's change their strategies. These are the mixed strategies that against the other person's player is as good as any strategy. Okay, so there's no better column strategy against the row player, and there's no better row strategy against the current column player. Okay, so in some sense, we're going to think about this another way. We're going to say, what if we let's think about this. Let's force the column player to go first. If the column player goes first, then the row player gets to go. So the column player announces their mixed strategy. And then the role player gets to choose the best strategy he wants. Let's think of the value of that kind of program. It's a program. So the Y player, the column player picks the strategy over the columns, which is Y. And then after you do that, then the role player gets to pick the best strategy it gets. And that, let's call the value of this process R. Okay? So that's where it's sort of an advantage to the row, right? Because the row gets to see the column player's entire strategy. And this is, and vice versa, this is an advantage for the column because we're making the row player announce their strategy. That's what the X player does. So weak duality says, well, look, the row player is an advantage is an advantage for the row. So in some sense, this number ought to be bigger than C, who R is trying to maximize. The row is trying to maximize. So the value of this game should be larger than the value of this game, right? Sort of trivially, because the value of C, the column player has the advantage. So he's going to minimize. So he does, its value must be lower. So in some sense, what you're thinking of, you can think of this as a paradigm of defense. I'm playing defense. The person who goes first says, I want to prevent this. If Y goes first, he wants to prevent the row player from getting good value. If he announces his strategy, he wants to say, there's no good offense for the column the row player, because the row player goes second. And now in situation C, in this other situation where the row player announces a strategy, they want to announce a strategy where the column player can't do better. Okay, can't do too well, right? That's what he's doing. He's trying to say, okay, I'm going to play in sort of rock, paper, scissors. If I announce I'm only going to play rock, that's my distribution. The Y player will go to town and win every time. Okay, so if R is less than C, then the column player, if in fact R is less than C, then the column player can play YR as YC. Whatever value he gets, the column player played here could be played here, and this strategy is good against every X player, because here this X can be chosen after this guy. So whatever this guy chooses here, this Y is at least as good as here. So that says that this is a proof by contradiction. If you say that if R is less than C, then the column player can just play Y sub R in this place, and Y sub C would be at least as good as R. Okay, so at equilibrium, what we have is that the payoff, we have this payoff, right? That's X, T, A, Y star. Let's call it star. Okay? So now if you look at this payoff, we can just think of part of the payoff, which is A, Y star. And that is essentially a column vector, right? And now in each one of these places, that's telling you the payoff for playing that row. Okay, after you do this, if Y star announces their strategy, if the column player announces their strategy as Y star, now the payoffs are just A times Y star for each row. Okay, that gives you the payoff here. And now X star, well, the X has no incentive to change. So we know that for all of these values, they must be less than or equal to V. Okay? Because if they didn't, then if one of these values was bigger than V, then there would be a better play than for X star that will give you a value that's larger than V. It could just play the pure distribution. The pure distribution is just a distribution that only plays wide option. It will play the maximum value option, which may be better than this X star, if there was a value bigger than V. So we know that this vector, the column vector, all the entries are less than or equal to V, the row payoffs. Okay, so that tells you that in this case, that this Y star gives you an upper bound. It says, here's a Y star here that can be used here, where the payoff for R is less than the value of V, less than the payoff for this particular equilibrium point. Okay, so that's the payoff. X star, A, Y star, and R which is equal to V, which is greater than or equal to R, because you can use this Y star in this place here, and get the right, no X is going to do too well, right? Because every entry in this vector is small, and the row is trying to maximize. Okay, and similarly, each column player is greater than or equal to V by the same argument. If some column player was less than, if against this row strategy, some column gave you a value less than V, then the column player would play that. Okay, and that tells you that this value is less than or equal to C. Again, you can use this X star in this place, and then no Y, it does very well, because every entry of this vector is greater than or equal to V, so no distribution over these entries can give you a value that's less than V, because all of them are at least V. So that tells you this thing is at least bigger than V, bigger than or equal to V. So this tells you that R is less than or equal to V, which is less than or equal to C, which tells you when if there is an equilibrium point, if there is this sort of magic object where neither player has an incentive to change, it tells you that, oh, if there exists such an object, then in fact these two programs, which look very different, right? The Y has the advantage. It looks like Y has the advantage here, and X has the advantage here. Whoever goes second gets to see the other people's mixed strategy, so it gets to play. It gets a lot more knowledge than the first guy. So you would think they do better, but in fact, these values, if there exists an equilibrium point, the values of these two programs are the same. That is called von Neumann's min-max theorem, and you can see why it's min-max, right? You can switch the mins and maxes in this form against these games, and somehow it works out that the values here are the same. Okay? So strong duality, all it says is there is an equilibrium point. And that says, von Neumann's theorem says there exists one. If there is an equilibrium point, I just argued that R and C are the same, and the strong duality theorem for two-person games is that there is an equilibrium point. It's a little bit analogous to linear programming. And therefore, these two programs always have the same value. So it's weird that these two players don't. There exist strategies for Y, so that X doesn't get too much. There exists a strategy for X where Y doesn't get too much, and the values each one of them get are equal. Okay, so let's look at this example. So this is rock, paper, scissors. Here, rock against rock, neither person pays. Rock against paper, rock pays paper 1, or the column paper pays rock -1, which means that in some sense, if you pay somebody negative, then they're actually giving you money. Okay, so this is the matrix for that. Rock ties with rock. Rock loses to paper. Rock beats scissors. Okay, gets the point. That's the row. The row is maximizing. So how do you play? This is how you play, right? Rock, paper, scissors. What you do is you play, the row player will play all equal probability. Right, you play each rock, paper, scissors with equal probability. The column player plays each strategy with equal probability. Okay, the mixed strategy, now they're playing distributions over strategies. That's what I'm saying when I'm saying mixed strategy. Pure strategy, now again, is each player plays a single strategy. Okay, just to see. So these are sort of in equilibrium. You see no incentive to change, right? So no matter what, against this strategy, say the column player goes second, it really makes no difference whether the column player plays this one, or plays this one. They win 1/3 of the time, and that's it. And they lose 1/3 of the time, and they tie 1/3 of the time. So the average is, it doesn't matter what strategy they play. So the value is, so this strategy is as good as any strategy against this strategy when you do 1/3, 1/3, 1/3. But when both of these guys are playing these strategies, neither one has an incentive to change. So this is also an equilibrium point. Okay, so here's another possibility. There's another row has an extra strategy. They're cheating. So what the cheating strategy doesn't always win, but it ties with rock and scissors, and it beats paper. So scissors or no rock. Okay, so the payoff matrix looks like this, right? So now you have this extra strategy for the row, and the row wins if the column plays scissors. Okay, this is cheat. So the column knows that rows cheats. In this setting, it's not like there's the cheating is subterfuge. It's like he knows that strategy in this world, the setup, the world we're talking about, is we know that the row can cheat. And now the question is, why would you play? Well, row is column's advisor. The advisor likes to win, so maybe the column player has to let the advisor win. Boss or the boss or whatever favorite setting you had. But the point is there an equilibrium pair? What is an equilibrium pair again? It's a strategy where a pair of strategies where neither have an incentive to change, right? Here it says if the row plays X star, whatever Y does, it can't do better than what it's doing in this strategy. And whatever if Y star plays this strategy, whatever X does, it can't do better than what it's doing currently. Okay? Says you fix Y, you force them to stick to the strategy and let X do whatever they want. They still can't do better. That's what this is saying. So that's when things are in equilibrium. Okay, so in some sense, no row is better, right? That's what we said before, and no column is better than the value of the game. In some sense, it says that X star only plays strategies that correspond to the maximum values achieved in this vector, and vice versa. It says Y star only plays columns which have minimum values in this vector because the column is trying to minimize. Okay, so let's see what it looks like here. Let's see. Let me illustrate. I illustrated an equilibrium strategy with rock, paper, scissors. Let's do it with rock, paper, scissors, and playing the boss or playing your advisor or something. Okay, so let's think of these strategies. So the column player plays the first column with probability 1/3, the second with 1/2, and the third with 1/6, and the row player plays with these probabilities sort of written here. Okay, what's the payoff? So it's a weighted average of pure strategies. So the row player does 1/3 with one probability 1/3. He's playing the strategy 1. What's the value of this pure strategy? Well, the value of this pure strategy is the column player plays this column with probability 1/3, this column with probability -1, and this column with probability 1/6. Okay, so if the column player plays this, the row wins 1. That's here. If the column player plays the second column, which he plays with probability 1/2, the row player loses 1. And if the column player plays the first column, which he does with probability 1/3, neither win. Okay, so the value of this strategy is -1/3. Okay, so it's bad for the row. What about the value of the next strategy? I'm just doing the same thing. I'm evaluating what is this? It's 1/3 times 1, 1/2 times 0, and 1/6 times -1. And that's 1/6. So the row player won't ever play this strategy because the row player is trying to maximize. So it won't play this strategy because this is just worse for it than this. It's trying to make it bigger, right? And so on. We can look at it. We can sort of do this calculation for all the columns, all the rows. And now the payoff is, now we're going to say, well, it's 0 times this first strategy because the row player plays this first strategy with probability 0, and its expected payoff with the first strategy is -1/3. He plays the second strategy with probability 1/3, right? And then he gets a payoff of 1/6. And this third strategy with probability 1/6, and he gets a payoff of 1/6. Now notice he's only playing strategies that are equal. They tie in how good they are. They're the maximum value. So this is just a property of equilibrium. Is you would never play a strategy if you played this strategy. Clearly, the row player, it would not be in equilibrium, because if he played this strategy with more than probability 1, that would be worse than moving that probability mass over to these guys where you're winning 1/6 on average. Here you're losing 1/3 on average. Okay. So the column player, every column payoff is 1/6. So both are playing. You can do the check for the column player that they're also have no incentive to change. These are equilibrium strategies. So notice notice that, yeah, that's this 0. You don't play strategies that are bad for you in equilibrium. And that's sort of analogous to this complementary slackness that we saw in linear programming. Okay? So why do you play more than one? Why, in that sense, why is either one playing more than one? Well, you want to limit the opponent playoff. The reason that the row player spreads this out is it's sort of trying to make sure that the column player never has a good option, right? I mean, I could always play rock, but against somebody else playing 1/3, 1/3, 1/3, but they're going to see me doing that. So I better play rock, paper, scissors with 1/3, 1/3, 1/3. Okay? So now the column player can play a distribution over all the columns because every column is payoff is 1/6, and that's just a calculation. You just sum these up times the probabilities here. You just take the dot product of this vector times this vector, and that's the column player's payoff for this column, and so on, right? It's just x a, and you get a vector which is like this, and all of these values are 1/6. Okay. Okay, so that's an example. So, does an equilibrium pair always exist? That's a question. We'll prove that later in the class. Okay, so now one other thing to notice is the equilibrium value is unique. So for a zero-sum game, the row maximizes strategy is an m-dimensional vector x, and the column has an n-dimensional vector y. Okay, and now the payoff is this expression. And the Nash equilibrium is these things where neither player has a better response against others. So if there's an equilibrium, there's no disadvantage in announcing your strategy, right? That's what it says. So I want to claim that all equilibrium points have the same payoff. Okay, so why? I'm going to assume for the sake of contradiction that there are two equilibriums. X1, Y1 are equilibriums, and X2, Y2 are equilibriums. But that tells you that since xi in equilibrium, it only plays the best strategies. It says the max value after you look at this. So after you look at the y strategy, you get a column. A times y is a vector. And that vector corresponds to the payoff for each row. And x is only going to play the best ones here. So the maximum values in this vector. And that the maximum value here has to be higher than the maximum value here because x only plays those things. Because xi is 0 on the non-best rows. And the best rows here are maximizing because the row is maximizing. So it says the maximum value in this vector is bigger than the maximum value in this vector. So the best row is worse under y2, right? This is smaller. Okay, so the column player should say, well, why am I playing y1? Here, even against x1, y2 is better than against x1 because the maximum value is lower. So therefore, the column player is not actually playing in equilibrium. He has an incentive to change. He will change over to y2 even against y1 because the maximum entry of a times y2 is smaller, and every x can't be better. Any distribution over these rows can't be better than the maximum value, the maximum expected value from that row. So x1, y1 is not an equilibrium, and that's a contradiction. So that tells you that all equilibrium points for zero-sum games have the same payoff function. Okay, so now what does this have to do with this linear programming? So the idea is that a matrix A, we're gonna have some notation here. These are the rows. A sub I is a row. A of super of with parentheses i's is a column. Okay. So the row player minimizes C. Okay, it's trying to minimize C. So it's saying, I want to announce a strategy X where the columns, the dot product of X with the column vectors are large for every column. Okay, larger than Z. And I want to make it as large as possible because the column goes second. Once this is really XT times A. You're saying every one of the entries here should be larger than Z, and then no matter what Y does, whatever distribution they do over this vector, their value has to be at least Z. So which is good for the row. The row is trying to maximize. And moreover, the sum of the xi's is equal to 1, meaning it's a probability distribution, and of course probabilities can only be positive. Okay, and this is similar. R is min Z. Here, A times Y should be less than Z. and the sum of yi's is equal to 1. I got to fix the typos here. Okay, so zero-sum games are, in some sense, it says here that zero-sum games, you can solve them. You can find equilibrium points by solving these two linear programs. Okay, it's very cool, that the connection here. And by the way, with some work, you can see that these are duals. And then this the notion of the strong duality theorem for zero-sum games it follows from the strong duality theorem for linear programs. Okay, so in fact, you can show that the zero-sum games are at least as powerful as linear programs as well. This is saying the linear programs are sort of more powerful, at least as powerful as zero-sum games. But with some work recently, actually, surprisingly recently, that somebody showed this. Okay, so in the simplex algorithm, in some sense, was developed by Danzig in America, in the U.S., and Kantorovich in the Soviet Union, and in the 30s. So for many years, that was the best thing. They did it in practice, but it's sort of a Kantorovich is interesting. He's a hero of the Soviet Union. He went under the siege of Petersburg. They had to build this lake froze, and they could deliver supplies over that lake. And Kantorovich is the one who organized the logistics of that. And as you see, linear programs are good for organizing logistics. So he was strongly motivated to develop this sort of thing, and he used this sort of thing in it's called the Ice Road to save the people in St. Petersburg. Okay, and Hachian is also Russian. He came up with this ellipsoid method that will also solve this. It's like a multi-dimensional version of binary search, but it's sort of not really that. It's sort of related to that. Okay, and it's been impractical so far. In practice, it doesn't seem to be effective. The simplex method is still better. The Carmarker developed these interior point methods, which seem to be both good in practice and also have polynomial time bounds for convergence or getting to the right answer. So that's also best codes are still based on one of these two things. Sometimes one is better than the other. It depends on the problem. Kellner and Spielman showed that simplex is actually polynomial on most linear programs, or programs that are slightly perturbed. It will actually have a polynomial time run time. Okay, so that sort of maybe explains the performance in practice. Okay, so now finally, to wrap up linear program, we're going to say the linear programs solve many problems. So it's, we keep seeing problem after problem that we can phrase as a linear program, right? We saw that already. But we want to say, well, is that always true? I mean, it seems like does it do everything? There is a sense in which it's true, and let me explain that to you. Well, it's really applicable. I mean, you can make a joke. It's so applicable that it's bigger than the house or something. I don't know. Okay, so let's think about this problem called circuit evaluation, and I'm going to show you that linear programming. You can write a linear program given a circuit. So you're given a circuit, which is a DAG, a directed acyclic graph of Boolean gates. 2 input and or gates and 1 input not gates, and true and false inputs. So what is the output of a specified output gate? That is the problem. You're given the circuit and you're asked, what is the output? Okay, so here's an example. What's the output of this gate? Well, what's the output of this gate? What is really the value? Well, true and false gives you false. False and true gives you true because it's or. Not true gives you false. But or of true and false gives you true. Not of false gives you true. And of true and true gives you true. So the output is true. Okay? So now let me translate the circuit thing into a linear program. Okay? So I'm going to make a variable for each gate. The output of the gate is going to be xg. And the output is either going to be between 0 and 1. Gate G is a true gate if xg is equal to 1. Okay? Xg is a false gate if xg is equal to 0. The value is false. So we're translating from this circuit problem, which has true, false values, to numbers for these variables that correspond to the output. Okay, so now let's try to simulate sort of the notion of an OR gate using these variables. So each one of these has a variable. There's an xh prime, an xh, and an xg. Okay, that's what we're going to work with. Okay, so xg has to be greater than xh, right? I mean, it says if this is true, which means it's 1, then this output better be greater than 1. Okay, so that's all this is saying. And it's also true for if it's true for h prime. If this is 1, then the output better be greater than 1. Better be true. That's what this is saying. Moreover, if both of these are 0 or false, this better be false. So this says 0 plus 0, so xg has to be 0 because it has to be in this range. Okay, so it sort of makes it these constraints force the output of this thing to behave correctly with respect to 0 and 1 inputs. Okay, and for an AND gate, you can do similar things. xg is less than or equal to xh. xg is less than or equal to xh prime, which says that if either one of these is false, then xg has to be false. If both of them are true, then xg can be 1. It can be 1, but now you have to force it to be 1. So now you say xg is bigger than 1. If it's true, this is 1, this is 1, so that's 2 minus 1, so it's bigger than or equal to 1. So it says the value of the output is at least 1 if both of the inputs are also 1, or the value of the output is true if both the inputs are true. And NOT gates are kind of easy. Switching 0 and 1 is just subtracting the value of the input. Okay, so here now we know this variable x0 is 1 if and only if the circuit evaluates it true, so you would just maximize x0. And then you would see if that value is 1 to see if the circuit has an output of 1. Okay, so the circuit value is completely general because in some sense this is what 61C tells you. It tells you how to build a computer from circuits, right? So a computer program, so those circuits are put together, and now you have a clock, and the whole computer is a circuit. One step is running that circuit. Now, one step you run the circuit, and then the next step you take that whole circuit, which is the whole computer, and you put it after as the input. You put the previous outputs from the memory from the previous step into this circuit, which is a computer, and then you have a new state for the memory. So each level is a circuit for a whole computer. So it's a little silly, right? Computers are pretty big, but there's some finite size, or there's some size that has to do with the size of the input. So the number of levels is the number of steps. So the circuit value problems sort of model computation, like in this very abstract theoretical sense. And it's not efficient, but in any constant factor sense. But it's sort of very general. So linear programs can model any polynomial time problem. So this is a stupid thing to do, but it says that in some sense these linear programs are very general because they can kind of simulate a computer. Okay, so later in a couple of lectures we'll talk about NP completeness and talk about these kinds of reductions more. Okay, lectures in a minute. I'll let you go over and check for yourself to see whether you understand all these words and map it to the concepts we talked about in lecture. Okay, thank you.